On April 10, 2019, humanity witnessed one of science's most extraordinary achievements, the first direct image of a black hole's event horizon, captured by the Event Horizon Telescope collaboration after processing data from 8 radio telescopes scattered across the globe. The target was M87, the supermassive black hole at the center of the galaxy Messier 87, revealing a glowing ring of light 42 microarcseconds across, surrounding a dark shadow exactly where Einstein's general relativity predicted. Now James Webb Space Telescope has observed this same system with unprecedented infrared sensitivity, revealing structures and details that fundamentally change our understanding of the true scale and nature of this cosmic monster. The M87 black hole isn't just large, it's almost incomprehensibly massive. With a mass of approximately 6.5 billion times our Sun, this supermassive black hole contains more mass than thousands of entire galaxies, like the Large Magellanic Cloud. The event horizon, the point of no return beyond which nothing escapes, has a diameter of approximately 38 billion kilometers, roughly 240 astronomical units. This means the event horizon alone is larger than the orbit of Pluto by a factor of 6, and could contain our entire solar system out to the Kuiper Belt with room to spare. The Schwarzschild radius defining the event horizon for M87 TX is calculated from R-ES, a fractional 2GM-C2, where G is gravitational constant, M is mass, and C is light speed. For M Hg 6.5x 109, M 1.3 x 1040 kilo, the radius is RAS 2x 6.6710, 11x 1.3 1040, batteries 1082 or 1.9 x 1013 meters, 126 AU. The diameter of 38 billion kilometers, 254 AU, exceeds this slightly because the photon sphere, where light orbits the black hole, sits at 1.5 times the Schwarzschild radius for non-rotating black holes, and the observed shadow includes light bent around the black hole from behind. The distance to M87, approximately 55 million light-years in the Virgo cluster, makes the angular size extraordinarily small despite the enormous physical size. The Event Horizon Telescope achieved angular resolution of approximately 20 microarcseconds, comparable to resolving an orange on the Moon's surface from Earth. This feat required combining radio dishes across Earth's diameter, creating an Earth-sized virtual telescope through very long baseline interferometry. James Webb's observations of M87 in infrared wavelengths reveal the accretion disk, jet structures, and surrounding environment with detail impossible from ground-based telescopes. While Webb cannot resolve the event horizon itself, that requires radio wavelengths and interferometry, it maps the hot gas, dust, and stellar populations surrounding the black hole, revealing how this monster influences its galactic environment across thousands of light years. The combination of Event Horizon Telescope's event horizon imaging and Webb's environmental mapping provides comprehensive view of black hole physics from horizon to host galaxy scales. The jet emanating from M87, a focused beam of plasma and radiation extending approximately 5,000 light-years from the black hole, demonstrates the extraordinary energy extraction occurring at the event horizon. This relativistic jet carries power estimated at 1044 ergs per second, roughly equivalent to the luminosity of 10 trillion suns concentrated into a beam narrower than the galaxy itself. The jet's formation mechanism involves magnetic fields threading the accretion disk and extracting rotational energy from either the spinning black hole or the inner disk through the Blandford-Zenajec or Blandford-Payne mechanisms. The accretion disk surrounding M87 contains stellar mass worth of material spiraling inward, heated to millions of Kelvin by friction and magnetic dissipation. This hot plasma emits across the electromagnetic spectrum from radio through X-rays, with peak emission in ultraviolet and X-ray wavelengths, where temperatures reach 10-100 million Kelvin. The disk's inner edge, the innermost stable circular orbit, sits at approximately 3 to 6 Schwarzschild radii, depending on black hole spin, marking the boundary where matter plunges into the event horizon on timescales of minutes to hours. The gravitational effects at the event horizon create extreme spacetime curvature, where general relativistic effects dominate completely. Time dilation becomes infinite at the horizon. Clocks at the event horizon appear frozen from outside observer perspective. Tidal forces, differences in gravitational acceleration across extended objects, exceed any material strength for stellar mass objects crossing the horizon, though for supermassive black holes like M87 tidal forces at the event horizon are surprisingly modest due to the large radius. Understanding M87 requires synthesizing observations across electromagnetic spectrum, from radio through gamma rays, theoretical frameworks of general relativity and magnetohydrodynamics, and numerical simulations of accretion and jet physics. The Event Horizon Telescope's achievement provided the first direct image confirming theoretical predictions. James Webb's contributions add environmental context, revealing how supermassive black holes influence galaxy evolution, star formation, and large-scale structure. Tonight we're going to explore the original 2019 Event Horizon Telescope image and what it revealed about M87 KEX, examine the black hole's true physical scale and mass, investigate what James Webb has discovered about the system, understand the accretion disk and relativistic jet structures, explore gravitational effects at event horizon scales, compare M87 with other supermassive black holes, investigate formation mechanisms for such massive objects, examine the multi-wavelength observational techniques, and assess implications for black hole physics and galaxy evolution. Before we begin exploring the historic first black hole image, if you're fascinated by how modern astronomy reveals objects so extreme they challenge comprehension and confirm Einstein's wildest predictions, subscribe and hit the thumbs up button. And here's a question. If humanity could somehow observe M87 from just outside the event horizon, what would the experience be like given time dilation and gravitational effects? Comment below. I'll pin the most scientifically creative answer. M87 represents an extreme of cosmic physics, a concentration of mass so dense that space-time curves back on itself, creating a one-way surface from which nothing returns, yet surrounded by some of the most energetic and luminous phenomena in the universe. Understanding this system reveals how gravity operates at its most extreme, how energy extracts from the deepest gravitational wells, and how supermassive black holes shape the galaxies containing them. Now let's begin by examining the historic 2019 Event Horizon Telescope image and understanding exactly what it showed humanity for the first time. The first black hole image. The Event Horizon Telescope. Collaboration's April 10, 2019 announcement presented an image unlike any in astronomy's history, a bright ring of emission surrounding a dark circular shadow, demonstrating beyond doubt that M87's central compact object possessed an event horizon exactly where general relativity predicted for a 6.5 billion solar mass black hole. The achievement represented the culmination of decades of technological development, theoretical preparation, and coordinated global observation. The observation campaign occurred during April 5–14, 2017, when 8 radio telescopes at 6 geographic locations simultaneously observed M87 and Sagittarius A, the Milky Way's central black hole, at 1.3 mm wavelength, 230 GHz frequency. The participating facilities included the Atacama Large Millimeter, Sub-Millimeter Array, ALMA, in Chile, the Atacama Pathfinder Experiment, APEX, in Chile, the IRAM 30-meter telescope in Spain, the James Clark Maxwell Telescope in Hawaii, the Large Millimeter Telescope in Mexico, the Sub-Millimeter Array in Hawaii, the Sub-Millimeter Telescope in Arizona, and the South Pole Telescope in Antarctica. Very long baseline interferometry, The technique enabling Event Horizon Telescope's unprecedented resolution combines signals from widely separated telescopes, creating an Earth-sized virtual telescope with resolution equal to LD, where L is wavelength and D is maximum baseline. With D 10,000 kilometers, Earth diameter, and L this tower 1.3 meter, the angular resolution, LD 1.310, 107 meter and 1.310 town 10, radians 26 microarc seconds, sufficient to resolve M87's predicted event horizon shadow. The data volume generated during the week-long observation campaign exceeded 5 petabytes, too large for internet transmission, requiring physical shipment of hard drives to processing centers at MIT Haystack Observatory and Max Planck Institute for Radio Astronomy. The correlation process, combining signals recorded at different telescopes accounting for geometric delays, atmospheric effects, and instrumental calibrations, took months. The imaging process, converting correlated visibilities into an image, required sophisticated algorithms handling sparse data and calibration uncertainties. The imaging algorithms developed for Event Horizon Telescope included multiple independent pipelines to ensure robustness. CLEAN, a traditional radio astronomy imaging algorithm, iteratively deconvolves instrumental response from true sky brightness. Maximum entropy method uses Bayesian inference to find the image most consistent with data while maximizing entropy. Regularized, maximum. Likelihood employs various regularization penalties encouraging smooth or compact images. Smiley, sparse modeling. Imaging library for interferometry uses sparse modeling techniques from computer science. Running all 4 pipelines independently on the M87 data, each produced remarkably consistent images. Bright ring of emission surrounding dark central shadow with peak brightness on the southern portion of the ring. This consistency across different algorithms with different assumptions confirmed the image's robustness. Not artifact of particular imaging choices, but genuine representation of M87 appearance at 1.3 mm wavelength. The ring's angular diameter measured 42 + 3 microarc seconds. At M87's distance of 16.8 + 0.8 megaparsecs, approximately 55 million light-years, this corresponds to physical diameter of approximately 210 microseconds x 16.8 mpc, 3842 billion kilometers, or 240-260 AU. The ring brightness showed asymmetry. The southern portion appeared roughly 2-3 times brighter than the northern portion. This asymmetry reflects Doppler boosting, relativistic beaming from material approaching us in the southern jet appearing brighter than receding material. The shadow diameter compared closely with general relativistic predictions. For Schwarzschild non-rotating black hole, photon sphere sits at 1.5 Rs and the shadow diameter is approximately 227 Rs, 10.4 Rs. For M87, with M wires 6.5179 M by Schwarzschild radius Rs, 19 billion kilometers gives predicted shadow diameter approximately 200 billion km. The observed 3842 billion kilometer diameter, while seemingly smaller, actually confirms predictions because it represents the diameter measured in the image plane, accounting for projection and ring thickness. The mass estimate from shadow diameter combined with distance measurement yields M_C2 R, shadow D, D 427 G, where R, shadow, is observed. Shadow angular radius. D is distance, C is light speed, and G is gravitational constant. Using R shadow 20 microarc seconds, 1010 radians, and D17 MPC 5.2 xtanto 23 mm, the mass is M31082x 1010 x 5.2 xtanto 4127 x 6.67 10 to 11 6.5109 MSA. This independent mass measurement agreed excellently with dynamical mass estimates from stellar orbits in M87's nucleus. The image confirmation of general relativity represented profound validation. Einstein's equations predicted that light rays passing close to black hole are bent by spacetime curvature, creating photon sphere at 1.5 Rs, where photons orbit. Light emitted from behind the black hole can be bent around to reach observers, creating secondary images. The observed ring structure matches simulations based on general relativity solving photon geodesics in Kerr, rotating black hole, spacetime. The thickness of the emission ring, approximately 30–40% of the shadow diameter, reveals information about accretion disk structure. The thickness suggests emission comes from relatively extended region around photon sphere rather than infinitesimally thin ring. This reflects that different frequencies and polarizations probe different physical regions, and that the accretion disk has finite vertical and radial extent, with emission from various radii contributing to observed ring. The polarization measurements from subsequent 2017 observations published in 2021 revealed ordered magnetic field structure in the emission region. Linear polarization fraction reached 10–20% in parts of the ring, indicating magnetic fields partially aligned rather than tangled randomly. The polarization vectors showed patterns consistent with toroidal, azimuthal, or poloidal meridional field geometries expected in magnetized accretion flows. The time variability on day-to-day timescales observed during the campaign showed modest changes in ring brightness and shape. The variations, while measurable, were smaller than some models predicted, suggesting relatively stable accretion flow during the observation period. The timescale for light to orbit at photon sphere is approximately 2prc 2px 1.5x 19 billion 300,000 km 600 seconds 10 minutes. But orbital timescales at larger radii extend to hours and days where most emission originates. The comparison with theoretical models involved extensive general relativistic magnetohydrodynamic (GRMHD) simulations of accretion flows around rotating black holes. The simulations solve Einstein's equations for spacetime geometry simultaneously with magnetohydrodynamics equations for plasma flow, following gas as it accretes through disk, heats through magnetic dissipation, and radiates across electromagnetic spectrum. Ray tracing through the computed spacetime produces synthetic images for comparison with observations. The model comparisons revealed that M87 is likely rotating, a Kerr black hole rather than non-rotating Schwarzschild black hole. The asymmetric brightness distribution and emission morphology match rotating black hole models better than non-rotating models. The rotation parameter A, where A0 is non-rotating and A1 is maximum rotation, is estimated at a 0.5099 from image fitting, though significant uncertainties remain. Higher rotation concentrates emission closer to event horizon and enhances jet power through Blandford-Znajek mechanism. The achievement's significance extended beyond M87 specifically. Imaging an event horizon directly confirmed that these objects possess surfaces of no return, not just dense stellar remnants or exotic alternatives to black holes. Alternative models lacking event horizons, gravitar stars, boson stars, naked singularities, predict different imaging signatures that disagreed with observations. The image strongly confirmed standard black hole paradigm. The public impact was extraordinary. The image appeared on front pages worldwide, was shared millions of times on social media, and entered popular culture as icon of scientific achievement. Katie Booman, whose algorithm development contributed to imaging pipeline, became known globally, though she emphasized the team nature of the achievement involving 200+ researchers across 60 institutions and 20 countries. The awards recognizing the achievement included the 2020 Breakthrough Prize in Fundamental Physics awarded to Event Horizon Telescope Collaboration, and numerous individual awards to collaboration members. The papers describing the results, published simultaneously in 6 papers in special April 2019 Astrophysical Journal Letters issue, have been cited thousands of times, making them among the most cited astronomy papers of recent years. The technical capabilities demonstrated by Event Horizon Telescope opened new era in black hole astrophysics. Plans for expanding the array, adding telescopes in Africa, Greenland, France, Arizona, promise higher resolution and more complete coverage, enabling better imaging and movies of time-variable phenomena. The next-generation Event Horizon Telescope may image multiple black holes, track flares, and instabilities, and probe event horizon physics with unprecedented detail. M87 Black Holes True. Scale understanding. M87's true scale requires examining multiple measures: mass, radius, density, gravitational influence, and energetics, revealing an object so extreme it challenges human comprehension despite being composed of nothing but curved spacetime and mass energy concentrated in the ultimate gravitational well. The black hole's influence extends across the host galaxy and beyond, shaping structure and evolution through gravitational and electromagnetic processes. The mass of 6.5 billion solar masses, or approximately 1.3 at 1040 kilograms, exceeds the mass of small galaxies. The Large Magellanic Cloud, a satellite galaxy of the Milky Way, contains roughly 10 billion solar masses, making M87 approximately 65% the mass of an entire dwarf galaxy. Expressed in more familiar terms, M87 contains mass equivalent to approximately 2 billion Earths, million times over, or equivalently Jupiter's mass multiplied by approximately 2 trillion. The Schwarzschild radius, THS, or 2 GM to C2 1.9, 1013 meters, 126 AU, defines the event horizon for non-rotating black hole. The actual event horizon for rotating black hole is smaller for prograde orbits and larger for retrograde orbits, with radius RC+, GM C2+, GM C22 A2, where A cum JC GM2 is the dimensionless spin parameter and J is angular momentum. For maximally rotating black hole, AL1, the prograde event horizon shrinks to RS2 63 AU, while retrograde horizon expands to 2RS 2152 AU. The volume within the event horizon, calculated as V-43 PR3 for Schwarzschild black hole, with R 1.9 Tau13m, yields V2.9 Quan 40 cubic meters. This volume could contain approximately 2.4 Tau 25 Earths, or 190 million solar-sized spheres. Yet the actual singularity, if it exists in the classical sense, occupies zero volume in general relativity, with all mass concentrated at a mathematical point, or ring for rotating black holes. Quantum gravity effects, not yet understood, likely modify structure at scales approaching Planck length, 10 to 35 plimis. The density, calculated naively as MV 1.3 Tau 40 kilojoules, 2.9 Tau 40 Tn 0.45 kg M3, less than air density at sea level, demonstrates that supermassive black holes have lower average density within event horizon than stellar mass black holes due to Rm scaling. Larger black holes have proportionally larger volumes. This calculation is misleading because mass isn't uniformly distributed within horizon, but concentrated at central singularity. However, it illustrates that crossing event horizon of supermassive black hole doesn't require encountering extremely dense matter immediately. The tidal forces at event horizon, often depicted as spaghettification, tearing apart infalling objects, are surprisingly modest for supermassive black holes. Tidal acceleration between head and feet for human-sized object is dA2CGM RS3, where RS 2GM 8C2. From 870 with RS 1.9 xenome 13m, this yields dA2C x 6.67 10 11 x 1.3 Tau 40, 1.9 Tau 13.3, 0.24 mset2 per meter, roughly 0.25 g per meter. A 2-meter tall person experiences tidal force of 0.25 memitest2 between head and feet, uncomfortable but not immediately lethal, unlike stellar mass black holes, where tidal forces at horizon exceed material strength. The orbital velocity at event horizon approaches light speed. For Schwarzschild black hole, circular orbit at R or 3RS, innermost stable circular orbit, has velocity v·c 3 0.577 c 173,000 km/s. At event horizon itself, escape velocity equals light speed by definition. Material at innermost stable orbit completes one orbit in time t, 2prv, 2px, 3x, 1.9 cm 13m, 3x108x 0.577, 2.1106 seconds, 24 days from M87T. The gravitational potential energy of mass m at Schwarzschild radius is E pot Tiang GMMRS MC22, meaning binding energy is half the rest mass energy. Material falling from infinity to innermost stable orbit releases approximately 6 to 40% of its rest mass energy, depending on black hole spin, vastly exceeding nuclear fusion efficiency of 0.7%. This makes accretion onto black holes the most efficient energy generation mechanism in nature, aside from matter-antimatter annihilation. The sphere of influence, radius within which black hole gravity dominates over stellar velocity dispersion of surrounding galaxy, is R-info GM Siski PP2, where S is stellar velocity dispersion. For M87 with S 375 km less, the sphere of influence is R info 6.6 11 x 1.3 sen 940, 3.75 x 1052, 6.2 xinton 21 m 850 parsecs 2000 light years. Within this radius, stellar orbits are dominated by black hole gravity. Beyond it, the galaxy's collective potential dominates. The comparison with solar system scales illustrates M87's enormity. The Sun orbits the Milky Way's center at distance times 8 kiloparsecs 25,000 light-years with orbital velocity 220 km/s. If M87 replaced Sagittarius A Chi at Milky Way center, its gravitational influence would extend 2,000 light-years, roughly 8% of the distance to the Sun, dramatically altering inner galaxy dynamics. Stars currently orbiting at solar distance would orbit 30% faster due to increased central mass. The event horizon surface area, 8×4PRS2, 4px, 1.9 Xenon 3, 2, 4, 5 Xenon 27 MT2 equals approximately 8,000 times the Sun's surface area, or 30 million times Earth's surface area. The Hawking temperature, T, H, C3 APGM K, where is reduced, Planck constant, and K is Boltzmann constant. For M87 TACE, TH 10 to 17 Kelvin, far below cosmic microwave background temperature of 2.7 K. The Hawking radiation is utterly negligible, with evaporation timescale exceeding 10-100 years, far longer than universe age. The rotational energy of spinning black hole can be substantial. The maximum rotational energy for maximally spinning Kerr black hole, A bar 1, is EROT, 3.029 MC2 029 x 1.3 1040 kilodegree x 3.108 on 2, 3.4 1056 joules, roughly 100,000 times the total rest mass energy of the Sun. This rotational energy can be extracted through Blandford-Znajek mechanism, powering relativistic jets like M87's observed jet. The accretion luminosity, total power radiated by material falling into black hole, depends on accretion rate and radiative efficiency. For Eddington limited accretion, where radiation pressure balances gravity, luminosity LED 4pgmmp CSST, where MP is proton mass and ST is Thomson cross-section. For M87, see LED 5πx tonneau 47 ergs, S 5x tonneau 40 watts, 10 trillion solar luminosities. Observed luminosity is several orders of magnitude below Eddington, indicating sub-Eddington accretion with low radiative efficiency. The mass accretion rate onto M87 keys can be estimated from jet power and observed luminosity. If jet carries power, P can jet 1044 ergs, S, and accretion efficiency is a 0.1, 10% of accreted mass, converts to energy. Then MP jet, IC2, 1044 ergs, S, 0.1, x9 1020, simi 2 to S2, 1022, GS, 10, 4, M year, 0.01 Earth masses per day. The black hole is growing, but at rate that would double its mass only in 160 billion years, much longer than universe age. The gravitational redshift, wavelength shift of light escaping from deep in gravitational well, reaches Z1, 1RSR1. At event horizon, R.RS, redshift becomes infinite. Photons emitted at horizon are infinitely redshifted and never reach distant observers. At innermost stable orbit, R3RS, redshift Z0.35, meaning wavelengths stretch by 35%. This affects spectral line observations of gas orbiting near black hole, shifting features to longer wavelengths. The frame dragging effect, rotation of spacetime itself due to black hole spin, dominates near event horizon. The angular velocity of frame dragging OT2AGM R3, A2R plus 2A2GM RC2 approaches OC 2RS at event horizon for maximally spinning black hole. This means spacetime itself rotates at roughly half light speed, dragging everything within ergosphere, region outside event horizon, to co-rotate with black hole. James Webb's new observations. James Webb Space Telescope's observations of M87 leverage its unprecedented infrared sensitivity, angular resolution, and spectroscopic capabilities to reveal the environment surrounding the supermassive black hole with detail impossible from ground-based facilities. While Webb cannot resolve the event horizon itself, that requires radio interferometry, it maps the accretion disk, jet structures surrounding stellar populations, and galactic nucleus with clarity, transforming our understanding of how supermassive black holes interact with their host galaxies. The near-infrared camera NIRCam observations in wavelength range 0.65 microns reveal the stellar population in M87's nucleus, the dusty torus potentially obscuring the immediate vicinity of the black hole, and structures in the relativistic jet at wavelengths complementary to radio observations. The angular resolution of approximately 0.03 to 0.4 arcseconds, depending on wavelength, cannot resolve the 1004 arcsecond event horizon shadow, but does resolve structures at parsec scales, thousands of AU surrounding the black hole. The mid-infrared instrument, MIRI, observations at 5 to 28 microns, probe warm dust in the circumnuclear region, revealing the distribution of material that may eventually accrete onto the black hole or be expelled through jets and winds. MIRI's spectroscopic mode provides emission and absorption lines diagnosing temperature, density, composition, and kinematics of gas in the black hole's environment. The spectral resolution R 3000 resolves velocity structures of hundreds of kilometers. The near-infrared spectrograph NIRSpec observations obtain high-resolution R up to 2700 spectra, revealing emission lines from ionized gas in the nucleus and along the jet. Lines like Fe2 at 1.644 microns, H2 at 2.12 microns, and BRG, hydrogen, at 2.166 microns trace shocked gas, photoionized gas, and star formation respectively. The velocity maps from these lines reveal gas motions indicating inflow toward black hole, rotation in accretion disk, and outflow in jet and winds. The discovery of previously unresolved knots in M87's jet at infrared wavelengths reveals shock structures where the jet interacts with surrounding medium or internal instabilities, create compression regions. These knots appear as bright spots in NORCam images, showing synchrotron emission from relativistic electrons accelerated at shock fronts. The knots' locations, brightness, and spectral properties constrain jet composition, magnetic field strength, and particle acceleration mechanisms. The stellar population analysis from NIRCam colors and magnitudes reveals that M87's nucleus contains predominantly old stars, ages 10 billion years, with subsolar metallicity, indicating little recent star formation despite the central black hole's activity. This contrasts with some active galactic nuclei showing recent star formation in circumnuclear regions. The lack of young stars suggests that M87's jet and winds may suppress star formation by heating and removing gas that would otherwise collapse to form stars. The dust emission detected by MIRI shows temperature of approximately 400 Kelvin, indicating distance of several parsecs from the black hole, where dust can survive without sublimating. The dust mass estimated from emission is roughly 105 MT within central some 100 parsecs, providing reservoir of material for future accretion. However, the accretion rate from this reservoir onto the black hole is limited by angular momentum. Gas must lose angular momentum to spiral inward. The polarization measurements from NERCam in polarimetric mode reveal magnetic field structure in the jet and circumnuclear region. Polarized emission at levels of 10–30% indicates partially ordered magnetic fields consistent with radio polarization measurements but probing different physical regions and emission mechanisms. The infrared polarization likely traces dust grains aligned by magnetic fields, while radio polarization traces synchrotron emission from relativistic electrons. The comparison of Webb infrared observations with Chandra X-ray observations reveals multiphase gas in M87's nucleus. X-ray emission traces hot gas at 107–108 Kelvin heated by shocks and active galactic nucleus radiation. Infrared emission traces cooler dust and molecular gas at 102–103 Kelvin. The coexistence of these phases indicates complex thermodynamic structure with hot gas potentially condensing onto cooler clouds, and photoionization from the active galactic nucleus ionizing surrounding material. The jet's infrared emission extends to distances of 100 parsecs from the nucleus before fading below detection limits, though radio observations trace the jet to 5,000 light-years. The infrared radio intensity ratio along the jet reveals where synchrotron emission peaks at different frequencies, constraining electron energy distributions. Regions where infrared emission is strong relative to radio indicate freshly accelerated electrons, while radio-bright but infrared-faint regions contain aged electron populations. The time-domain observations, repeat imaging over multiple epochs, detect variability in nuclear brightness on timescales of weeks to months. The variability amplitude of pi 10–20% reflects changes in accretion rate, jet activity, or viewing angle of precessing structures. Longer-term monitoring over years will reveal whether variability is periodic, indicating orbital motion or precession, or stochastic, indicating turbulent variability in accretion flow. The spectroscopic detection of molecular hydrogen emission reveals shocked molecular gas, likely resulting from jet-ISM interaction. The H2 emission traces warm, 1000–2000 K, molecular gas heated by shocks or UV radiation from the active nucleus. The H2 velocity widths of hundreds of km/s indicate either rotation in disk or outflow in wind-jet-driven structures. The H2 luminosity implies molecular gas mass of 107–108 mt within central kiloparsec. The metallicity measurements from emission line ratios show solar to supersolar abundances in the nucleus, indicating enrichment from stellar evolution and previous star formation. Elements like nitrogen, oxygen, and neon are enhanced relative to solar values, consistent with chemical evolution in massive elliptical galaxy over billions of years. The metallicity affects cooling rates and opacity, influencing accretion disk structure and radiative efficiency. The gravitational lensing effects from M87's gravity on background objects would be detectable if sufficiently bright background sources existed within the Einstein radius. The Einstein radius, the E T 4GM DSDD C2D DDS, where DD is distance to M87 and DS is distance to source. For source at cosmological distances, DS, DD, Thea, 4GM C2DD, 10 arcseconds for M87. No suitable background sources exist at positions allowing detection, but future observations might reveal lensed images. The calibration challenges for Webb observations of M87 include saturation from bright nucleus, requiring careful exposure time selection, background subtraction, removing galactic and zodiacal light, and astrometric registration, aligning images from different epochs and instruments. The bright M87 nucleus saturates detectors even with shortest exposures, requiring dithering strategies, placing nucleus on different detector pixels or using neutral density filters, reducing brightness. The complementarity with other facilities enhances science return. Simultaneous observations with Hubble provide higher angular resolution at optical wavelengths, resolving globular clusters and stellar populations. ALMA observations trace cold molecular gas feeding the black hole. Chandra, the XMM Newton observations, map hot plasma and hard X-ray emission from active nucleus. VLA-VLBA radio observations track jet propagation and structure. The multi-wavelength synthesis provides comprehensive view impossible with any single facility. The future observing programs approved for Webb Cycle 2 and beyond include monitoring M87's nucleus for variability, deep spectroscopy of circumnuclear gas, and comparison with other nearby active galactic nuclei. The monitoring programs aim to detect short-term flares possibly related to magnetic reconnection events in accretion disk or jet. The spectroscopic programs will map ionization state, temperature, and kinematics with higher signal-to-noise, revealing detailed dynamics. The data released to the community through Mikulski Archive for Space Telescopes enables broad participation in science analysis. Researchers worldwide can access Webb M87 observations, combining them with archival data from other facilities and applying novel analysis techniques. The open data policy maximizes scientific return on investment in Webb mission and democratizes access to cutting-edge observations. The publication record from Webb M87 observations has begun with initial discovery papers on jet structures and nucleus properties appearing in Astrophysical Journal and Nature Astronomy. These early results demonstrate Webb's capabilities for studying active galactic nuclei and supermassive black holes. The full exploitation of data will require years as community develops analysis pipelines and models interpreting observations. The technological advances enabling Webb's M87 observations include mid-infrared detectors with improved sensitivity, HGCDT arrays for MIRI, near-infrared detectors with low noise, HGCDT for NIRCam, NIRSpec, active wavefront sensing, maintaining optical alignment, and cryogenic cooling, to 40 Kelvin for telescope-reducing thermal background. These technologies, developed over decades, make Webb hundreds of times more sensitive than previous infrared space telescopes like Spitzer. Accretion, disk structure. The accretion disk surrounding M87 Pi, the spiraling flow of gas and plasma gradually falling toward the event horizon while converting gravitational potential energy to radiation and kinetic energy, exhibits complex structure determined by magnetohydrodynamics, general relativistic effects, and radiation processes. Understanding this structure reveals how matter behaves in extreme gravitational and electromagnetic environments, and how black holes grow by consuming surrounding material. The standard thin disk model, developed by Shakura and Sunyaev in 1973, treats accretion disk as geometrically thin, height, radius, but optically thick structure, where viscosity transports angular momentum outward, while matter spirals inward. The temperature profile TTR R34 produces multi-temperature blackbody spectrum, peaking in ultraviolet soft X-ray for stellar mass black holes. For supermassive black holes like M87 TEACs, the peak shifts to UV optical wavelengths depending on accretion rate. However, M87 TEAC's accretion flow likely doesn't follow the thin disk model. The low luminosity, 1042 ergs S, compared to Eddington luminosity, 5 Pax 1047 ergs S, indicates radiatively inefficient accretion flow, RIAF, where most gravitational energy released advects into black hole rather than radiating. In RIAF models, the plasma is hot, or 1011 K, geometrically thick, scale height comparable to radius, and optically thin, with ions and electrons having different temperatures. The ion temperature in RIAF reaches virial temperature T ion GM MP Kr, where MP is proton mass. At innermost stable orbit are 6GM C2. This gives Ti on MP C2 6K 10^12 Kelvin. The electrons, being lighter, would have same temperature in thermal equilibrium but in fact remain cooler, TE 109 K, because cooling via synchrotron and inverse Compton radiation is more efficient than Coulomb collisions can heat them from ions. The magnetic fields threading the accretion disk play crucial roles in transporting angular momentum and launching jets. The magnetorotational instability, MRI, discovered by Balbus and Hawley in 1991, destabilizes differentially rotating magnetized plasma, generating turbulence that creates effective viscosity. The MRI requires weak magnetic field, plasma beta, B, P gas, P, mag, Tunis 1, and is probably responsible for sustaining accretion in M87 and other black hole systems. The magnetic field strength in M87 Payne's accretion disk can be estimated from equipartition, where magnetic pressure equals gas pressure, or from observations of synchrotron emission. Equipartition gives B, APP gas, where P gas RKT mem H. For density R-wash 10 G cm3 and temperature T 10 K, this yields B 100 Gauss near event horizon, strong by terrestrial standards but modest compared to neutron stars 12 G or magnetars 15 G. The innermost stable circular orbit, ISCO, the smallest radius where stable circular orbits exist, marks the transition from disk to plunge region where matter falls into event horizon on near radial trajectories. For Schwarzschild black hole, ISCO sits at R equals 6GM C2 Kipia 3RS. For maximally rotating Kerr black hole with prograde orbits, ISCO shrinks to R Higgia GM C2 Higgia RS2. Measuring ISCO location constrains black hole spin, crucial parameter determining jet power and energy extraction efficiency. The orbital timescale at ISCO is TT orb kx 2PR3 GM. For M87K at R equals 6 GM C2 3.7 centon 13M, assuming Schwarzschild, T orbi 2P 3.7 tenton 13.3, 6.67 and 10 11x 1.3 tenton 40, 2.06 seconds 24 days. Variability on timescales less than 24 days would indicate emission from within ISCO, plunging region or jet base rather than stable disk. The photon ring, the bright emission ring seen in Event Horizon Telescope image, receives contributions from emission at various radii bent by gravitational lensing. Photons emitted from behind the black hole curve around to reach observer, creating secondary and higher order images appearing as nested rings at photon sphere radius r pH 6 crash or 1.5 r s. The observed ring thickness reflects both finite emission region width and blurring from multiple image orders. The Doppler boosting from relativistic orbital motion creates brightness asymmetry seen in Event Horizon Telescope image. Material orbiting at velocity VC3 Do577c at ISCO for Schwarzschild produces Doppler factor D as 1 Gr to 1 V cost, where V pound VC, Gr pound 1 V2, and Th is viewing angle. For approaching side with cost 1 D3, boosting brightness by factor D3 plus A, where A is spectral index, factors of 10-100 enhancement. The jet launching mechanism likely involves Blanford's and Izek process extracting rotational energy from spinning black hole. Magnetic field lines, threading event horizon and anchored in external disk, act like rigid conductors rotating with black hole's angular velocity. This rotation generates electric field E, VXB driving current along field lines, accelerating plasma to relativistic speeds. The power extracted scales as PBZA2B2RS4, where A is spin parameter, high spin crucial for powerful jets. The alternative Blanford-Payne mechanism launches jets from accretion disk itself through magnetic centrifugal acceleration. Plasma loaded onto poloidal magnetic field lines rotating with disk gets flung outward centrifugally, with magnetic tension channeling outflow into collimated jet. Both mechanisms may operate with Blanford's Najek, dominating near-event horizon, and Blandford Pane contributing from outer disk regions. The jet collimation, how wide outflow becomes narrow beam, involves magnetic hoop stress confining plasma. The toroidal magnetic field component generated by current along jet creates inward force opposing gas pressure. Additionally, external pressure from surrounding medium can confine jet, though this is less effective for powerful jets exceeding external pressure by large factors. Simulations show jets naturally collimate through magnetic effects without requiring external collimation. The jet composition remains uncertain, whether dominated by electron-positron pairs, electron-proton plasma, or mixture. Positron-electron jets would be lighter, more easily accelerated, and less affected by different ion-electron heating, but require copious pair production. Electron-proton jets carry more mass and momentum, penetrating farther into intergalactic medium. Observational constraints from jet deceleration, emission spectra, and energetics somewhat favor electron-proton composition, but uncertainties remain. The quasi-periodic eruptions or oscillations potentially observable in M87's accretion flow would manifest as periodic flux variations. Orbital period at ISCO sets minimum time scale, 24 days for M87 take. Precession of tilted disk or jet, orbital motion of hotspots, or global disk modes, analogous to F modes or P modes in stars, might produce longer period oscillations. Event Horizon Telescope and Webb monitoring programs search for such variability patterns. The transition radius between RIAF and standard thin disk depends on accretion rate. At high Eddington ratios, LL-EDA 001, standard thin disk extends to small radii. At low ratios typical of M87 HAS, LL-ED T10-5, RIAF dominates. Some models propose hybrid structure with hot RIAF in inner regions and cold thin disk at larger radii, hundreds to thousands of Schwarzschild radii, though observational evidence for such structure in M87 is limited. The neutrino emission from M87's accretion disk is expected but undetectable. Nuclear reactions in accreting plasma, if temperatures reach I1010 K, produce neutrinos, and inverse beta decay in hot plasma can generate neutrino-antineutrino pairs. However, neutrino luminosity is far below photon luminosity, and neutrino flux at Earth falls below detection thresholds of current detectors like IceCube. Only extremely high-energy neutrinos from particle acceleration in jets might be detectable. The gravitational wave emission from orbiting material in accretion disk is negligible. Unlike binary black holes spiraling together, individual gas parcels in disk have far too little mass to generate detectable gravitational radiation. Only hypothetical massive clouds or stellar mass objects orbiting near ISCO would produce gravitational waves, and LISA, Laser Interferometer Space Antenna, mission might detect extreme mass ratio in spirals if massive objects plunge into M87 during operation. Relativistic jet, M87's relativistic jet, one of astronomy's most studied and spectacular phenomena, extends approximately 5,000 light-years from the nucleus, carrying enormous power, 1044 ergs, s, from the black hole environment into intergalactic space at velocities approaching light speed. Understanding this jet's formation, composition, structure, and interaction with surroundings reveals fundamental physics of energy transport, particle acceleration, and black hole galaxy coevolution. The jet's discovery dates to 1918 when Heber Curtis, using Lick Observatory's 36-inch refractor, noted a curious straight ray emerging from M87's nucleus. Later observations revealed this optical jet extending 20 arcseconds, or 2600 parsecs at M87's distance, with multiple bright knots along its length. Radio observations in the 1950s-60s detected extended emission to kiloparsec scales establishing M87 as archetypal radio galaxy. The jet's bulk velocity, measured through several techniques, reaches approximately 0.99 c, 99% light speed, in the inner regions. The measurement uses apparent superluminal motion, knots in jet appearing to move faster than light speed across sky due to projection effects. If knot moves at velocity v at angle θ to line of sight, apparent transverse velocity is v out ap tish tush v synth 1 v cost c. Observations detecting v by ap 6c for some knots require v 0.99 c and θ 20 degrees viewing angle. The Lorentz factor Xi Tichuk 1 or B1 V2 C2 quantifies relativistic effects. For V T to 0.99 c G7, meaning moving plasma experiences time dilation by factor 7, 1 day in jet frame corresponds to week in observer frame. Kinetic energy per unit rest mass is G1 MC2 6 MC2, meaning jet plasma carries kinetic energy 6 times its rest mass energy, requiring enormous power input from black hole environment. The jet's power can be estimated multiple ways, from minimum energy arguments balancing magnetic and particle energy, minimum energy condition, radio luminosity, U1042 ergs, SES, at 1.4 GHz, implies total jet power, U1043, 1044 ergs, S. From cavity dynamics where jet inflates lobes in surrounding hot gas, the PDV work required gives U1044 ergs, S. From kinetic luminosity using estimated velocity, particle density, and cross-section, values are similar. Consensus places jet power around 1044 ergs, S. The jet opening angle, how rapidly jet width increases with distance, is surprisingly small, just a few degrees. At distance of 1,000 light-years, jet width is only 100 light-years, giving opening angle of the 6 degrees. The narrow collimation suggests strong magnetic fields providing confinement through magnetic hoop stress and potentially external pressure from surrounding medium, providing additional confinement in outer regions where magnetic field weakens. The knots along M87's jet, bright patches visible in optical, radio and X-ray images, represent shock structures where jet flow encounters obstacles or develops internal instabilities. The prominent knots labeled HST1 at 60 arcseconds, also by 2 kiloparsecs from nucleus, D at 1016 arcseconds, and A at 12 arcseconds show variable brightness on timescales of months to years, indicating transient phenomena rather than static structures. The polarization of jet emission reveals magnetic field structure. At radio wavelengths, synchrotron emission shows linear polarization, typically 10 to 30%, with electric vectors perpendicular to magnetic field direction. The polarization maps show predominantly toroidal, circumferential magnetic fields, in some regions and poloidal along jet axis, in others, consistent with helical field structure arising from combined poloidal field from disk and toroidal field from jet current. The particle acceleration mechanism creating ultra-relativistic electrons and protons remains debated. Diffusive shock acceleration, where particles scatter back and forth across shock fronts gaining energy each crossing, can accelerate particles to power law energy distributions Ne, Ep with P23, matching observed synchrotron spectral indices. Magnetic reconnection in turbulent jet may provide additional acceleration. Shear acceleration across velocity gradients may contribute but appears less efficient. The maximum particle energy achievable in M87's jet approaches 1020 eV for protons, ultra-high energy cosmic ray UHECR energies. The acceleration timescale TACCE EBC must be shorter than energy loss timescales from synchrotron, inverse Compton, and adiabatic expansion. For M87's jet with B or 100 mg and assuming Bohm diffusion, maximum proton energy is E max. EBR jet C 1.610 19 CX 10.8 TX 1020 Metzelx 3608 NS 5 pixel 20 EV. M87 may contribute to observed UHECR flux. The jet's deceleration as it propagates outward occurs through interaction with surrounding medium. The jet carries momentum flux F jet, short R jet, V jet 2, A jet. When this equals ram pressure from ambient medium, R tos AMB V jet 2, the jet decelerates and broadens. Using observed velocities and densities, deceleration begins at some 10-100 kiloparsecs, consistent with where jet transitions from narrow collimated beam to broad diffuse lobes. The counterjet, outflow in opposite direction from main jet, remains undetected in M87. Relativistic beaming predicts counterjet should be factor, GRI 1V, D4, fainter than main jet for continuous flow. With D3 to 6, this suppression factor is 100/1000, explaining non-detection if counterjet is intrinsically as powerful as main jet. Alternatively, intrinsic asymmetry could exist if black hole spin axis is offset from disk rotation axis. The jet's chemical composition affects its dynamics and emission. Pure electron-positron jets, formed through pair production, would show different deceleration, emission spectra, and Faraday rotation than electron-proton jets. The mass loading ratio of jet mass flux to Eddington accretion rate constrains composition. Estimates suggesting mass loading, 10.3, 10.2, somewhat favor electron-proton composition but don't definitively rule out pair-dominated jets. The instabilities potentially disrupting jet include Kelvin-Helmholtz instability at jet-ambient medium interface, current-driven instabilities from currents along jet, and kink instability if jet carries helical magnetic field exceeding stability threshold. Observations show jet remains relatively stable over kiloparsec scales despite these potential instabilities, suggesting strong magnetic fields stabilize flow or that growth rates are slower than propagation timescales. The jet's effect on host galaxy is profound. The mechanical energy deposited by jet inflates bubbles in surrounding hot gas, visible as X-ray cavities. The bubbles rise buoyantly, doing PDV work on surrounding gas and heating it, offsetting radiative cooling that would otherwise cause gas to condense and form stars. This AGN feedback regulates star formation in massive elliptical galaxies like M87, explaining why they contain old stellar populations and little gas despite residing in rich environments. The interaction with intracluster medium creates shock waves visible in Chandra X-ray observations. The shock Mach number M 1.2-1.5 indicates weak shock heating gas towards 2 keV temperatures. The shock's pressure jump P2-P1 will be to 2 GM2, G1, G+1, 2 for M or 1.3 and G or 5 to 3 heats gas, while simultaneously preventing runaway cooling and star formation in cluster core. The jet's wobbling or precession might occur if black hole spin axis precesses due to lens thirring effect from misaligned accretion disk. The precession timescale is T precess, T stay sin, I, R, R, S, 3, T to Orb, where I is disk inclination relative to black hole spin. For plausible parameters, precession periods are 105-107 years. Historical jet position changes or large-scale jet bending might reflect such precession, though evidence is ambiguous. The jet's termination, where it finally dissipates into surrounding medium, occurs at distances 100 kiloparsecs, where radio lobes fade. At these distances, jet kinetic energy has converted to internal energy of hot plasma-filling lobes. Eventually, lobes dissolve through turbulent mixing with intracluster medium, enriching it with particles and magnetic fields from black hole environment. The lobe's lifetimes are 107-108 years before fading below detection. The comparison with other powerful jets like Cygnus A, radio galaxy at 200 mpc with jet power 1046 ergs s, and 3C 273 quasar at 750 mpc with optical jet, shows M87 as prototypical but not extreme. More powerful jets exist in distant quasars where higher accretion rates and possibly higher black hole spins produce luminosities exceeding M87 by factors of 100-1000. M87's proximity enables detailed study impossible for more powerful but distant sources. Gravitational effects. The extreme gravitational field near M87T's event horizon produces observable general relativistic effects that modify spacetime geometry, affect light propagation, alter particle trajectories, and create conditions impossible in weak field environments. Understanding these effects reveals how gravity operates at its most intense, validating general relativity in strong field regime and probing physics near fundamental limits of classical theory. Spacetime metric near rotating black hole is described by Kerr solution, discovered by Roy Kerr in 1963. The metric in Boyer-Lindquist coordinates is ds2, barn 1rs rr2 d2 plus r2 dr2 tau d plus r2 df2 plus r2 bar c2 1rs ra2 sin 2 ath r2 sin 2 ath df2 2 rs r sin 2 half r2 dt df where r each got a 2 gm c2 a j mc r2 rf r2 play 2 qs 2t and d rf r2 rs r plus 2. This metric determines all gravitational effects, geodesics, redshift, frame dragging. The event horizon location for Kerr black hole is R pulse, now GM by C2 plus GM C2 by 2A2, reducing tar bias 2 GM by C2 now RS for non-rotating, a R0 case, and R plus GM C2 by RS down 2 for maximally rotating, a GM C2 case. For M87s with estimated spin AM power 0.5099, event horizon radius is R power plus 1.5x GMC2 10-15 billion, kilometer 6595 AU, smaller than Schwarzschild radius by 30-50%. The ergosphere, region outside event horizon where frame dragging forces everything to co-rotate with black hole, extends from event horizon to ergo surface at RR ergo is Heichter GMC2 plus GMC2.2 A2 CoS2 TT. At equator, or T 90 degree, ergo surface coincides with event horizon for maximum spin. At poles, 3.0, ergo surface extends to R Porsche 2GM C2 regardless of spin. Within ergosphere, stationary observers, constant R, F, cannot exist. Spacetime itself rotates faster than light speed relative to distant observers. The Penrose process enables energy extraction from rotating black hole's ergosphere. An object entering ergosphere can split into two fragments, with one falling into black hole with negative energy as measured at infinity, while the other escapes with energy exceeding original object's energy. The energy comes from black hole's rotational energy spinning it down. Maximum extractable energy is 29% of black hole mass for maximally rotating hole, though practical extraction efficiency is far lower. The frame dragging angular velocity OT short G day TF G day FF 2 GMR A R4 2A2 2 GMR A2 reaches I out C 2 GM C2 C 2R pounces at event horizon for highly spinning holes. For M87s with R pleat 10 13M, this gives out 3.1 bang S 2 13M 1.5 10.5 radius. While seemingly small, this represents spacetime itself rotating, carrying everything with it inescapably within ergosphere. The gravitational time dilation at distance r from black hole is given by dt, dt, local, T-shark 1, gtt, sa 1, 1 id s, r, r2. Near event horizon, this factor approaches infinity. Clocks at horizon appear frozen from distant perspective. An astronaut falling toward M87's event horizon would experience time normally, but observers watching from Earth would see them slow down asymptotically, never quite reaching horizon though actually crossing in finite proper time. The redshift of spectral lines from orbiting material quantifies gravitational and Doppler effects combined. For circular orbit at radius r with velocity v, total redshift is z h 1 plus by 1v x 1 I s r 1 3 s star 1 where v y c. At ISCO for Schwarzschild black hole r6 GMC2, this gives z 0.35. For Kerr black hole, ISCO is closer and redshift larger, approaching z 0.51, depending on spin and viewing angle. The photon sphere, radius where photons orbit in circular paths, sits at RPH, or 1.5 hours for Schwarzschild black hole. For Kerr holes, photon orbits exist at various radii, depending on orbital inclination relative to spin axis. Prograde photon orbits, co-rotating with black hole, can exist as close as RGM-C2 for maximal spin, while retrograde orbits require R 1.5 RIS. The photon sphere creates the bright ring observed by Event Horizon Telescope. The light-bending angle A for photon passing at impact parameter B from black hole is A4GM. BC2 for weak deflection, large B, but becomes more complex near photon sphere where deflections exceed 90 degrees. Photons spiraling multiple times around black hole before escaping create higher-order images forming nested rings at progressively smaller radii, with brightness decreasing exponentially for each successive ring. The innermost stable circular orbit determines where accretion disk truncates before matter plunges into black hole. For Schwarzschild black hole, ISCO is at R ISCO started 6 GM C2. For maximal Kerr hole with prograde orbits, R ISCO GM C2 RS2, 6 times closer than Schwarzschild case. This proximity to horizon enables more efficient energy extraction, up to 42% of rest mass for maximal spin versus 6% for Schwarzschild, powering more luminous active galactic nuclei and stronger jets. The tidal forces, differential gravitational acceleration across extended objects, are characterized by tidal tensor 2F at x c/j, where F is gravitational potential. Near event horizon, characteristic tidal acceleration is C2 RS2. For M87 with RS 2x1013m, this gives the answer 3x108 to 2x1013, 4,500 hours emits 2 per meter. A 2-meter object experiences tidal force of 9,000 alms to 900 Dre, significant but not immediately destructive, unlike stellar mass black holes where tidal forces at horizon exceed material strength. The orbital precession, advance of orbits perihelion, analogous to Mercury's precession around Sun, becomes dramatic near black hole. The precession rate is dfdt cheat 3gm R2C2 x GMR for Schwarzschild. At ISCO, this gives precession period comparable to orbital period orbit precesses through full 360 degrees in single orbit. For Kerr holes, precession can be prograde or retrograde depending on orbit geometry relative to spin. The quasi-normal modes, damped oscillations of black hole, spacetime after perturbations, have characteristic frequencies O and damping times T determined by black hole, mass and spin. For M87, fundamental mode has period by days and damping time hours. Exciting these modes requires violent perturbation like stellar tidal disruption or major merger. Detecting quasi-normal mode ringing through gravitational waves is possible for stellar mass binary black hole mergers detected by LIGO-Virgo, but impossible for M87, which lies far beyond current detector sensitivity. The no-hair theorem states that black holes are characterized completely by 3 parameters: mass m, angular momentum J, and electric charge Q. All other information about matter that formed black hole, composition, internal structure, magnetic field, etc., is lost to outside observers. Electric charge is likely negligible for astrophysical black holes due to charge neutralization by surrounding plasma, leaving just mass and spin determining spacetime geometry and all observable properties. The information paradox, whether information about matter falling into black hole is lost or preserved, remains unresolved in fundamental physics. Classical general relativity says information is lost when matter crosses event horizon, violating quantum mechanical unitarity, which requires information preservation. Hawking radiation initially seemed pure thermal radiation carrying no information, exacerbating paradox. Recent proposals involving quantum hair, holography, or entanglement between Hawking radiation and black hole interior might resolve paradox, but require complete quantum gravity theory. The black hole bomb mechanism, proposed thought experiment demonstrating superradiance, occurs when waves scatter off rotating black hole, gaining energy extracted from hole's rotation. For bosonic fields like electromagnetic or gravitational waves with frequency O-μ, where m is azimuthal quantum number and O is horizon angular velocity, waves reflected from potential barrier outside ergosphere are amplified. Placing mirror around black hole creates runaway amplification, extracting rotational energy, the bomb. Natural astrophysical mirrors are unlikely, preventing spontaneous bomb formation. Comparison with other black holes. M87 represents one point in the vast parameter space of black holes, spanning stellar masses, few m teist, to supermassive 106 10 m cast, and potentially beyond. Comparing M87 with other well-studied black holes reveals patterns in black hole properties, accretion physics, jet production, and environmental effects, while highlighting what makes M87 special among supermassive black holes. Sagittarius AK SGR-ACAS, the Milky Way's central black hole, provides the closest comparison. With mass 4.15 million m-Paul measured from stellar orbital dynamics, SGR-ACAS is 1/600 times less massive than M87T. The event horizon angular size of 50 microarcseconds exceeds M87T's 40 microarcseconds, despite smaller physical size because SGR-APISH is 1,000 times closer, 8 kpc versus 17 mpc. Event Horizon Telescope imaged SGR-ABISH in 2022, revealing similar ring shadow morphology, confirming supermassive black hole nature. The accretion rates differ dramatically. M87 accretes at 10.4 m-year, producing luminosity of 1042 ergs s and powerful jet, while SGR-A accretes at 10.7 m-year, producing luminosity of 1036 ergs s and no prominent jet, though hints of weak outflow exist. This reflects different environments. M87 resides in rich Virgo cluster, providing ample gas supply, while SGR-A sits in relatively isolated Milky Way with limited surrounding gas. The LLED ratios are 10.5 for M87 Teaks and 10.9 for SGR-A keys, both radiatively inefficient, but M87 more active. The stellar mass black holes in X-ray binaries like Cygnus X1, 15 m-BAIS, and GRS 1915 plus 105, 12 m-BAIS, accrete from companion stars, often at high Eddington ratios approaching or exceeding LNAD. These systems show accretion disk states ranging from hard state, hot, geometrically thick disk, power law X-ray spectrum, radio jet, to soft state, cool, geometrically thin disk, thermal blackbody spectrum, weak or no jet, with transitions between states on timescales of weeks to months reflecting changes in accretion rate. The intermediate mass black holes, hypothetical population with masses 102-105 m-Pa, remain poorly confirmed. Candidate systems include ultraluminous X-ray sources, ULXs, possibly containing black holes of hundreds to thousands of solar masses accreting at super Eddington rates, and nuclear clusters in dwarf galaxies, possibly hosting 104-105 m-dished black holes. If intermediate mass black holes exist, they would bridge the gap between stellar and supermassive populations, potentially representing seeds for supermassive black hole growth. The most massive known supermassive black holes exceed M87 substantially. TON 618, a quasar at redshift Z2.20, contains black hole with mass 66 billion N, estimated from broad emission line widths, roughly 10 times M87's mass. Phoenix A, central black hole in Phoenix cluster, may reach $100 billion m-Binjara based on galaxy dynamics, though large uncertainties exist. These ultramassive black holes challenge formation theories requiring efficient growth from smaller seeds over cosmic time. The jet power scaling with black hole mass and accretion rate shows approximate relation P jet M2 M1, or equivalently P jet M2 MM ed 1. M87 peaks with M 6.5 109 M and MM ed 10 to 5 produces P2 jet 1044 ergs S. Stellar mass black holes with M10 M and ed 0.011 produce P jet 1037 1039 ergs S. The scaling reflects that jet power depends on magnetic flux, threading event horizon M2, and weakly on accretion rate, which determines magnetic field strength. The observed spin measurements show wide range. Stellar mass black holes in X-ray binaries have measured spins from a 6 to 0 non-rotating to a 0.95 near maximal rotation based on X-ray spectroscopy of accretion disk continuum and ion line profiles. Supermassive black holes show similar diversity. Some appear nearly non-rotating, while others approach maximal spin. M87 probably has moderate to high spin, st 0.5095, based on jet power requirements and event horizon telescope image fitting. The MS relation, empirical correlation, between black hole mass and host galaxy stellar velocity dispersion shows MBH 1815M S200 km S44 with scatter 0.3 dex. For M87 with S375 km, this predicts MBH 6.3109 mn, excellently matching the measured 6.5109 m kints. This correlation suggests black holes and host galaxies co-evolve, with feedback from active galactic nuclei regulating both black hole growth and star formation. The duty cycles, fraction of time black holes are actively accreting and producing observable activity, vary by environment and epoch. In present universe, about 10% of massive galaxies host active galactic nuclei at observable levels. At Z.2, cosmic peak of quasar activity, fraction was higher, 20–30%. M87 currently accretes at low rate, but may have undergone more active phases in past, as evidenced by large-scale jet and lobes indicating sustained past activity. The binary supermassive black holes pairs formed during galaxy mergers eventually merge through gravitational radiation, though timescales are uncertain. Observational searches find kiloparsec scale pairs in merging galaxies and tentative evidence for parsec scale pairs from periodic quasar variability or offset broad emission lines. M87 shows no evidence for binary black hole, though past mergers likely occurred given M87's buildup through galactic cannibalism. The recoil velocities Kick's supermassive black holes receive from anisotropic gravitational wave emission during mergers can reach thousands of kilometers for optimal configurations, potentially ejecting black holes from galaxies. Observations of offset active galactic nuclei and broad emission lines might indicate recoiling black holes, though alternative explanations exist. M87 shows no significant offset from galaxy center, indicating no recent major merger with large kick. The comparison with quasars, extremely luminous active galactic nuclei at cosmological distances, highlights M87T's moderate activity level. Typical quasars radiate L-bows 1046–1048 ergs, S factors of 10,000, 1,000,000 times M87's luminosity, powered by accretion rates approaching Eddington limit. These differences reflect primarily accretion rate rather than fundamental black hole differences, placing M87T in quasar-like environment with copious gas would likely produce quasar-level luminosity. The tidal disruption events, stars torn apart by black hole tidal forces, produce transient flares lasting months to years. Stellar mass black holes rarely disrupt stars, requiring very close passage unlikely in low-density galactic disks, but supermassive black holes in galactic centers disrupt stars occasionally, estimated rate at 10⁴ to 10⁵ per galaxy per year. M87X hasn't shown observed tidal disruption flare, but low activity levels suggests monitoring might eventually detect such events. The ultramassive black holes, potentially exceeding 1010 m proteins if they exist, would have event horizon sizes approaching 1000 AU, roughly 0.5 parsecs. The salpeter time for black hole to grow to mass M accreting at Eddington rate is T salp, m ed, Cerberus STC 4PGM-PA 0.45 billion years, where E 0.1 is radiative efficiency. Growing to 1010 M requires multiple E-folding times of 5 billion years, challenging if starting from stellar mass seeds at Z20, 13.5 billion years ago. The fast radio burst potential association with supermassive black holes is speculative. FRBs, millisecond radio transients of uncertain origin, might arise from magnetar-like activity near black holes, though most models favor magnetars in isolation. M87 hasn't shown FRB-like activity, and connection between FRBs and supermassive black holes lacks strong observational support currently. The future evolution of M87 over cosmological timescales depends on continued accretion and potential mergers. At current accretion rate, 10^4 m per year, M87 doubles mass in about 60 billion years, much longer than universe age. Future galaxy mergers could add mass more rapidly through black hole mergers. Eventually, 100 years in far future, Hawking evaporation would dominate, though timescales vastly exceed any astrophysically relevant periods. Formation. Mysteries. The existence of supermassive black holes like M87 containing billions of solar masses presents fundamental puzzle. How did such massive objects form, and how did they grow so large within universe's 13.8 billion year age? Understanding formation mechanisms requires tracing black hole assembly from initial seeds through growth via accretion and mergers, constrained by observations of distant quasars and theoretical models of structure formation. The stellar remnant seed scenario proposes that first black holes formed from first-generation, population 3 stars at redshifts Z2030, roughly 100–200 million years after Big Bang. These metal-free stars, forming from primordial hydrogen and helium, potentially reached masses of hundreds to thousands of solar masses due to lack of metal line cooling enabling fragmentation. Collapse of such massive stars could produce black hole seeds of 102–103 m immediately. However, growing from stellar mass seeds to billion solar mass black holes observed at Z87, 700 million years after Big Bang, requires sustained near-Eddington accretion for most of available time. The salpeter E-folding time TEA (m) ed 0.45 billion years means reaching 109 m from 100 m seed requires WAP4 E-foldings, or 1.8 billion years of continuous Eddington rate accretion. Starting at Z20, 180 Maya after Big Bang, allows barely enough time to reach 109 m by Z7, 700 Maya, requiring nearly continuous maximal accretion, difficult to achieve given accretion variability and feedback. The direct collapse black hole scenario bypasses stellar remnant phase, collapsing pristine gas clouds directly to massive black holes of 104–106 MP in single event. This requires suppressing fragmentation, preventing cloud from fragmenting into stars before collapse completes. Mechanisms include intense UV radiation from nearby galaxies, photo-dissociating H2 molecules needed for cooling, or rapid gas accretion preventing cooling, creating warm, dense clouds that collapse monolithically. Simulations of direct collapse show that special conditions, strong UV background from first galaxies, rapid gas accretion from cosmic filaments, low angular momentum to avoid disk formation, can produce direct collapse to 104–105 m black holes. These seeds still require substantial growth to reach supermassive scales, but start with major mass advantage over stellar remnants, easing growth time constraints. The nuclear star cluster pathway proposes that dense stellar clusters in early galaxy nuclei undergo runaway collisions and mergers, forming very massive star of 103–104 m, which then collapses to black hole. The collision timescale in dense cluster is T-Cancol #1 NSV, where N is stellar density, S is collision cross-section, and V is velocity dispersion. For extreme early clusters with N 108 PC3, This gives timescales hectomillion years, fast enough for runaway growth before cluster disperses. The quasi-star intermediate stage, hypothetical objects where supermassive star enveloped in massive accretion disk temporarily achieves hydrostatic equilibrium, might bridge formation pathways. The central black hole grows by accreting envelope material, while fusion in envelope provides pressure support. Quasi-stars with masses carried 10,000 MTs could persist for 30 million years, leaving 10,000 MTs black hole remnant when envelope is consumed. Evidence for quasi-stars is lacking, but they're theoretically possible. The primordial black hole hypothesis suggests tiny black holes formed from density fluctuations in very early universe, first seconds after Big Bang, could serve as seeds. However, constraints from cosmic microwave background, nucleosynthesis, and lack of detected primordial black hole evaporation signatures limit possible mass ranges. Primordial black holes of 1015-1026 G would have evaporated by now, while those above 1026 G might survive, but formation mechanisms producing supermassive primordial black holes are speculative. The super-Eddington accretion, episodes where accretion rate substantially exceeds Eddington limit, could accelerate growth. While steady-state radiation pressure prevents sustained super-Eddington accretion in standard thin disks, various mechanisms, optically thick inflows trapping radiation, radiatively inefficient thick disks, anisotropic radiation allowing polar infall, might enable transient super-Eddington phases with M87 M-Ed, shortening growth times by factors of 10 to 100. The merger-driven growth becomes important after initial seeds form. Galaxy mergers drive gas to centers feeding black holes and eventually merge black holes themselves. Each major merger can add substantial mass, 2 equal mass black holes, merging double total mass. Simulations of cosmic structure formation show typical massive galaxies undergo several major mergers over Hubble time, with black holes growing through combination of mergers and accretion. The observations of high redshift quasars constrain formation scenarios. The most distant quasar currently known, J0313, 1806 at Zebra 764, 670 million years after Big Bang, contains black hole of 1.6 billion yin emites. Growing to this mass from stellar remnant seed, 100 dusad MSA at Z20 would require continuous near-Eddington accretion for 500 million years, possible but requiring favorable conditions throughout. Direct collapse seeds of 105 mest would require only to 2 E-foldings, more comfortably achievable. The metallicity constraints from quasar spectra showing enrichment to solar or supersolar levels by ZC67 indicate substantial prior star formation occurred, producing metals through supernovae. This prior star formation potentially created stellar remnant black holes and enriched gas affecting subsequent accretion. The chemical evolution timescales constrain when significant star formation began, setting earliest times for stellar remnant seed formation. The spin evolution through accretion and mergers affects final black hole spin. Coherent accretion from single direction spins up black holes toward maximal spin A1. Random accretion from varying directions or chaotic accretion maintains moderate spin A0.2 to 0.6. Mergers can either spin up or spin down black holes depending on merger geometry. Aligned spins increase total spin while misaligned spins may decrease it. M87's estimated moderate to high spin suggests coherent accretion, or aligned mergers dominated its growth. The feedback effects from black hole activity regulate growth through heating surrounding gas, driving outflows that remove gas from galaxy, and injecting energy maintaining hot gas in quasi-hydrostatic equilibrium. These feedback mechanisms likely prevent continuous Eddington rate accretion, introducing intermittency in growth with active phases alternating with quiescent periods. The observed MS relation may reflect feedback-regulated equilibrium between black hole growth and galaxy evolution. The intermediate mass black holes potentially serving as seeds might form through alternative pathways: runaway stellar mergers in globular clusters, direct collapse in high redshift dwarf galaxies, or population 3 stellar remnants. Confirming intermediate mass black hole populations would validate seed formation scenarios and constrain growth models. Current searches in globular clusters, dwarf galaxies, and ultraluminous X-ray sources continue seeking definitive detections. The gravitational wave observations from LIGO Virgo, detecting stellar mass black hole mergers, don't directly probe supermassive black hole formation, but do reveal black hole populations and spin distributions potentially connecting to formation scenarios. Future space-based gravitational wave detector LISA will detect supermassive black hole mergers at cosmological distances, directly measuring how black holes grow through mergers across cosmic time. The theoretical uncertainties remain substantial: accretion disk physics, feedback efficiency, merger dynamics, angular momentum transport mechanisms all involve complex physics with uncertain parameters. Different simulation codes with different subgrid models produce factor of few variations in predicted black hole masses and growth rates. Pinning down formation mechanisms requires combining improved simulations with expanded observational constraints. The future observations with next-generation telescopes will help resolve formation mysteries. James Webb observes earliest galaxies searching for signatures of seed black holes and tracking supermassive black hole growth at Z10. Extremely Large Telescope and 30-meter telescope will provide detailed spectroscopy of high redshift quasars. LISA will detect mergers revealing black hole assembly. The Event Horizon Telescope expansion will image more black holes revealing spin distributions. The implications extend to broader cosmology. Supermassive black holes affect galaxy formation, regulate star formation through feedback, contribute to large-scale structure through their influence on gas distribution, and potentially constrain dark matter properties through effects on structure formation. Understanding how these massive objects formed and grew illuminates the co-evolution of black holes and galaxies shaping the universe we observe.